Good day to all of you. Today we shall study Kruskal's algorithm. By the end of this video session, you will come to know about what is Kruskal's algorithm and how it is used to find minimum cost spanning tree given any graph. Let's start the session. Kruskal's algorithm is used to find minimum cost spanning tree. In this algorithm, first we sort all the edges of the given graph in increasing order. Then it keeps on adding new edges and nodes in the MST, that is minimum cost spanning tree, if the newly added edge doesn't form a cycle. It picks the minimum weighted edge at first and maximum weighted edge at the last. What is minimum cost spanning tree? It is the subgraph of original graph. It is connected subgraph, has all the vertices of original graph. It doesn't have any cycles and parallel paths. It has smallest total weight of its edges. In the intermediate stage, it can be disconnected graph unlike Prim's algorithm. If the original graph has V vertices, minimum cost spanning tree also will have V vertices but V minus 1 edges. MST minimum cost spanning tree is the subgraph of given graph, having collection of only those edges that connects all the vertices with minimum sum of edge weights. Kruskal algorithm is greedy and has straightforward way to create a minimum spanning tree. Greedy algorithm means at every step it makes locally optimal choices, finding a global optimum solution. So in last video session we have studied Prim's algorithm. In Kruskal's algorithm, unlike Prim's, we take the edges in sorted order, that is in increasing order, then keep on adding new edges with minimum weights. Last one is the edge with maximum weight is added, that is the last one. So that is the difference between Prim's and Kruskal's, that is the first difference. Another difference here is in the intermediate stage, Kruskal algorithm can give disconnected subgraph. But in case of Prim's algorithm, in the intermediate stage also, the subgraph will always be connected graph. Connected means the vertices will be connected with the edges. Here in Kruskal's algorithm, they may be disconnected. Both are greedy algorithms, means at every step they make optimum solution. So in the problem, original graph is given. From that, minimum cost spanning tree means subgraph is found, which will have same vertices as the original graph but V minus 1 edges. The total edge weight will be minimum. That is why it is called as minimum cost spanning tree. So that we shall see through an example how using Kruskal's algorithm minimum cost spanning tree is found for the given original graph. Okay. So for solving we shall take this example. First let us see how Kruskal's algorithm works. The first step, sort all the edges in a non-decreasing order of their weight, means increasing order of their weight. Pick the smallest edge. Check if it forms a cycle with the spanning tree formed so far. If the cycle is not formed, include this edge, else discard it. Repeat step 2 until there are V minus 1 edges in the spanning tree. So it is possible to have different edges included in minimum spanning tree or minimum cost spanning tree for the same graph, but the total edge weight of the MST minimum cost spanning tree will be still same minimum value. So a problem can have different subgraphs as minimum cost spanning tree, but the minimum cost obtained, the total edge weight will be same. That is very important. So next we shall take up this original graph and solve for minimum cost spanning tree using Kruskal's algorithm. Okay. So example 1, the problem statement is find the minimum cost spanning tree using Kruskal's method having greedy approach for the graph given below, that is this. So in the first step of solution for the given graph, we have to observe that there are 6 vertices and totally number of edges is 9. So when we find minimum cost spanning tree, it will also have 6 vertices. So v equal to 6, but number of edges will be 6 minus 1, that is 5. Okay. As already mentioned, in the first step of solution, we have to sort the edges in the increasing order. So ED equal to 2. So this is the smallest. So another 2 is there. So BD edge, it has got weight 2. So this is BD edge, it has got weight 2. Then we have these two edges with 3. Then this is 4. That is what we have written. AB equal to 5, that is written here. Then BC edge, this is BC edge, that is with 6. AF with 7. Then FC with 8. So edges in increasing order of weights, they are written here. Okay. Next we'll take original graph, and to find subgraph we go on adding these edges in the increasing order of weights of the edges, and cycle should not be formed in the process. Okay. That procedure will have to continue till in the final subgraph we have v number of vertices and edges 5. Okay. V is equal to 6 and number of edges will be 5. First minimum weight edge is ED. So that is added. So next minimum weight is BD. So that is added. Next minimum weight is CD equal to 3. So CD is added. So next edge is AC equal to 3. So AC edge is added in the subgraph. So next edge is BE equal to 4. But if this time if you observe, if you connect BE here, it forms the cycle. Hence BE equal to 4 is not added in the subgraph. Okay. Similarly, next edge if you take AB equal to 5. So if you connect this, again cycle is going to be formed. Hence AB equal to 5 edge will not be added in the subgraph. Okay. Similarly, next edge BC equal to 6 if you take, if you connect that, then also cycle is formed. Hence this is not connected in the subgraph. Okay. Next edge is AF equal to 7. So AF equal to 7 is here. So it doesn't form any cycle. So it is connected. The last edge is FC equal to 8. So that is here. If you connect, if you observe, cycle is formed. Hence FC equal to 8, that edge is not connected in the subgraph. So if you see to this subgraph, that is minimum cost spanning tree graph, it has 6 vertices and edges is equal to 5. Hence we'll have to solve the procedure. If this is the given original graph, this is the subgraph, that is the minimum cost spanning tree found using Kruskal's greedy approach method, and the minimum cost is sum of all the weights of these connected edges. Okay, that comes out to be 17, and that completes the solution. I hope you understood. Thank you.